Okay, so let's start with identities and inverses, and let's just remind ourselves what the multiplicative identity is. Remember, it's the number that I can multiply by anything and not change its identity. So what do I multiply by A to give me A? The multiplicative identity is 1. Well, in matrices, I need to be able to do the same thing, so I need a matrix identity. A matrix identity of a 2 by 2 looks like this. Ones on the forward diagonal and zeros in the other holes. Okay, the identity of a 3 by 3 is ones in the forward diagonal and zeros in all of the other holes. That is the 3 by 3 identity. That's a 0. So, if you multiply a matrix and its inverse, you should end up with the identity. It's like multiplying 2/3 by its inverse. I should end up with 1, right? I'm going to erase that because that's a mess. Okay, so when I multiply a matrix by its inverse, I should end up with 1, which is the identity matrix. So this is a 2 by 2. This is a 2 by 2. These match, so my result is going to be a 2 by 2. So remember, I always create this blank one. This is first row, first column. So I'm going to multiply the first row times the first column. And what I'm going to get is 1 times 11 is 11, plus -5 times 2, which is the -10. Now I'm going to multiply the first row, second column. First row, second column to get this guy right here. So I get 1 times 5. 1 times 5 is 5, plus -5 times 1 is -5. Okay, now this guy is the second row, first column. Second row, first column to get this guy right here. So I'm going to multiply -2 by 11, which gives me -22, plus 11 times 2, which is 22. And that last position is the second row, the second column. So I'm going to multiply the second row by the second column to get this position. -2 times 5 gives me a -10. And 11 times 1 gives me 11. If I go ahead and add those, 11 plus -10, 5 plus -5, -22 plus 22, and -10 plus 11. So I have just verified that this and this are inverses of each other. Now the question is, how do I get an inverse? How do I get an inverse from a matrix? Okay, so we're going to look at A. Okay, this is A, B, C, D. A, C in the first row, B, D in the second row. This little guy is an inverse symbol. So the inverse of A is 1 over the determinant times what I call the flip-flop. Okay, what did I do? I flip-flopped A and D, just changed positions, and I changed the signs on B and C. So I'm going to multiply by 1 over the determinant times the flip-flop. So let's see what that does. So I'm going to multiply by 1 over the determinant. The determinant here is 11 minus 10. So that's 1, but we're going to go ahead, and now we're going to flip-flop. So I'm going to change the place of the 11 and the 1, and I'm going to change the signs of the 2 and the 5. I'm going to multiply 1 over 1 times this matrix. This, don't forget, is called a scalar. I'm going to multiply each element by that guy, but since it's 1 over 1, nothing's going to change. So my inverse is going to be 11, 2, 5, 1. Let's look at this next one. So I'm going to multiply by 1 over the determinant, which is 6, minus 4. And times the flip-flop. So change the 3 and the 2, and change the sign on the -1 and the -4. This is 1/2 times the matrix 3, -1, -4, 2. So the inverse is going to be 3 over 2, -1 over 2. This is a -4, so -2 and 1. This would be my inverse. If the determinant equals 0, so if I get 0 down here, obviously I can't divide by 0. There is no inverse because this would be undefined. Therefore, it's called singular. Okay, so this first equation looks really easy, doesn't it? 2x equals 5. How do I solve that? Well, I divide by 2. Don't forget, I also multiply by the inverse. That's another way to solve it. So I'm going to get x equals 5 over 2. Well, to solve a matrix equation, and it might be helpful if you had these boxes around it, it would remind you that it's a matrix. To solve a matrix equation, I also will multiply by the inverse here and here. But multiplication is not, I'm going to say it again, not, one more time, not commutative. So in solving this, I'm going to multiply by the inverse of A times A, x equals the inverse of A times B. If I multiply the inverse of A times A, I would get the identity, which means 1. So I would have had 1x equals whatever this answer is when I multiply it out. But this is multiplied first. This must be multiplied first over here. Remember, the inverse of A times B is different than B times the inverse of A. Multiply first, multiply first. So let's solve this matrix equation. We're going to say this is matrix A, x equals matrix B. I want to solve for x. Matrix A times what matrix will give me matrix B? So the first thing I have to do is find the inverse of A. So let's just make sure we're keeping track. This is A, this is B. So I want to find the inverse of A. The inverse of A is 1 over the determinant, which is 6 times 3 minus 2 times 8, times the flip-flop. Switch the corners. I guess I'll say switch the forward corners, just change places and change the signs on the backwards corners. Okay, so this is 1/2 times these, so my inverse is going to be 3 over 2, -1, -4, and 3. That's my inverse. So I'm going to multiply the inverse of A in front of these matrices. Sorry, those numbers are so small. This is 3 over 2, -4, -1, and 3. If I multiply this side, what do I get? I should get the identity matrix, so I want you to pause and multiply those two. And you can see if you do the multiplication that I do get the inverse. This would be 1, 0, 0, 1. Okay, here's where everything's going to kind of start getting jumbled in your head, because don't forget, I'm doing 3/2 times 6 plus -4 times 2. The adding and subtracting, keeping, when do I add diagonals, when do I subtract diagonals, that's where you're going to have complications. Okay, so I do get the identity on the left side. Now I'm going to pause, and I need you to multiply out the right side. So I probably didn't pause long enough, sorry. I assume that you pause the computer when I say to pause. So my answer should be x equals this matrix. And if I multiply A times this matrix, I should get B. Here we go. Ready for a roller coaster? A roller coaster that you're going to throw up on afterwards. So, we're going to do an inverse of a 3 by 3. We are going to use the transpose cofactor method. So the first thing we need to do is we need to create what's called A sub C, which is the cofactor matrix. So the AC, A sub C, is the cofactor matrix where we're going to replace every element in the matrix with its minor and its associated sign. Okay, so here we go. A sub C. So this position right here is the first row, first column. So I'm looking at this guy right here. And remember, everything has an associated sign, so I'm going to put them in real quick. Plus, minus, plus, minus, plus, minus, plus, minus, plus. And there, we're halfway done. Okay, so this guy right here, we're going to replace this element with its minor. And remember, you find a minor by crossing off the row and column. And they're going to be the determinant. So this is going to be the determinant of 3, 0, 3, 8. Okay, where did I get that? I crossed off this row and this column. It leaves me with 3, 0, 3, 8. This 1, if I cross off the row and column associated with the 1, I have 5, 0, 4, 8. Okay, cross off the row and column for the negative 2. I have 5, 3, 4, 3. I'm going to do that for the next 2 rows. I'd like you to pause, and I want you to fill these in. Okay, so now check your answers really closely. Make sure all your signs are correct, and we'll go forward. Now, if you remember, these strong brackets mean determinant. So we're going to find the determinant in here. Remember, it's multiply, subtract, multiply. Okay, so this is 24 subtract 0. So I'm going to start breaking this down a little bit. I'm going to put my signs in again. Okay, and this is 24 subtract 0. And I have 40 subtract 0. So that's going to be 40, but the sign of that element is a negative. 15 subtract 12 would give me 3. Okay? I want you to pause and fill in the rest of this. Okay, now check your numbers. Be really careful, especially something like this. This is 0 subtract negative 10. So my determinant is 10, but my sign associated is a negative. So a negative times a positive gives me the negative 10 over here. Okay, this is my A sub C. What I'm going to do now real quick before the next screen is I'm going to create my A sub C to the T. T stands for transpose. And I'm going to put transpose definition in. So transpose means exchange every row for a column. So here's what we're going to do. We're going to take this row, the first row, and I'm going to make it the first column. 24, negative 40, and 3. Second row becomes second column. Third row becomes third column. And that's what we're going to pick up with on the next screen. Okay, and I just realized I made a mistake. This element right here should not be negative 2. It should be 8 minus negative 6. So 8 plus 6, which would be 14. So it should be negative 14. So I'm just going to change it right here. I'm going to change it in my ACT. This should be this one right here, because the second row becomes the second column, so that negative 14 goes top here. So that should be a negative 14. Sorry about that. All right, so to find the inverse of A, if it's a 3 by 3, I still have to do 1 over the determinant and multiply that by A sub C to the T, the cofactor matrix transposed. The cofactor matrix transposed. Here is my cofactor matrix transposed. I now need to find the determinant of this. Okay, how do you find a determinant? You do diagonals. So since you know how to do that, I'm going to pause and I'm going to do the determinant underneath. You guys go ahead and try this and check your answer. Don't forget, we're finding the determinant of A, not of A cofactor transposed. So finding the determinant of A, don't forget, you multiply your red diagonals, add them together. You multiply your blue diagonals, add them together, and take red, subtract blue, and you get a determinant of 2. So I'm going to do 1 over the determinant. So the inverse is 1/2 times that ACT. And 1/2, again, would be called a scalar. So if I multiply everything by 1/2, I'm going to get and that is the inverse of A. Wasn't that fun?